Hello, welcome back everybody. Today in geometry, we're looking at this last section of translation slash mapping, which is going to be called symmetry. So this is going to be, I guess, the last part of it. So, here we go. Buckle your seatbelt then. So let's go ahead and first define what a symmetry is going to be, okay? A symmetry is going to be anything where, sorry, not anything. A symmetry is specifically a mapping, okay? And it's a mapping that is not an identity that will map a figure to itself. So, for example, what that means is that you have a figure and then you are going to do some sort of mapping where the result is that it goes back to the original picture. So, for example, over here on the lower picture, let's say that you have this sad face over here, right? If I draw a vertical line right there, right down the middle, then you can see that any point on that sad face, if you reflect it about the vertical line, is going to give you a point that is going to be back in the original mapping, basically back onto the sad face. Basically, the best way to explain it is that if you fold it, right, if you fold the face across the vertical line, then it's just going to be the opposite symmetric picture. So it's exactly identical in that case. Then there is this picture, then there's this one over here on the middle. Now, for the middle part, unfortunately, there's no line symmetry that we have in the first one, but what we can do is we can do a rotation symmetry. So let's say that we have this point over here, which is the intersection between the two squares. If I rotate it, right, if I rotate the figure about that point using a half rotation, or maybe like say a full rotation, then that is going to give me back the original picture as well. So that in itself is also going to be considered a symmetry. Now, for the first one, as we said, this is going to be called a line symmetry because you are going to create a symmetry about a line where it goes back to the original figure then. So here we'll go ahead and call it that, okay? So that is called line symmetry. And this one is called a point symmetry then, because what we're doing is we're taking a point and then we're rotating it about that point. So as a result, we are then going to go back to the original picture. Now, this one you have to be very careful though. The rotation, right, about point O, and where O is going to be this right here, by 180 degrees right here. That's basically kind of like a half turn right here, which is equivalent to a half turn. This is going to be the point symmetry. I actually, unfortunately, cannot use the rotation of O of 360 degrees because if you take anything and rotate 360 degrees, that right there does go back to the original picture, but unfortunately, that is an identity because for any shape, you can always rotate by 360 and it will still go back to yourself. So because this is an identity, I cannot consider that as a point symmetry then, okay? Now, in the last picture right here, where you have this cross, you actually have multiple different types of symmetry that you can use. You can use a line symmetry or you can use a point symmetry and it will go back to the same thing. So for example, here, let's say that you can have a line symmetry that's horizontal and you can see if you flip it or you fold it across that line, then you get basically the same shape. You can do it vertically also, and then that'll give you the same shape. Heck, you can even do it diagonally right there, and you can do it the same shape. So there are definitely more than one line symmetry in this case. And then in addition to that, we also have a point symmetry because right in the middle right there, if you rotate it, right, by that point, which we'll go ahead and call O once again, by 90 degrees, that will definitely work out. If you rotate it by 180 degrees, that will work. If you rotate it by 270 degrees, that will work. If you do it by 360, that will work too. But again, that is going to be an identity, so we don't actually consider that one. So there it is. So you can see from our illustration that there are two types of symmetry right here, the line symmetry and the point symmetry. So let's go ahead and give a formal definition to each one of those then, okay? So we say that a line symmetry is basically a reflection because you're going to reflect it about the line that maps the figure back to itself. So any point that's on the figure and then you reflect it and it becomes a point that is going to be in the original figure, not necessarily the same point, then that means that it's a line symmetry then. So here, the reflection of line K that maps any figure A to itself, then it's going to be fine, okay? Next, we can talk about then the point symmetry, right? A point symmetry is then defined as a rotation about a point that maps a figure back to itself. So here we have R, and then we rotate about the point, and then we have theta, and then it maps A back into A. And we should note that theta, right? Actually using the wrong pin, theta over here cannot equal to 0 or 360 degrees because those are identities, which is not something that I actually want to use according to the formal definition. Okay. All right. So now let's keep going. So beyond the line symmetry and point symmetry, there is something called the translational symmetry. So translational symmetry, translation, that basically means you're shifting it left and right, up and down, and so forth. Is it possible to shift something so then that way you go back to the original mapping? And the answer is yes, depending on what that thing is that you're actually mapping. What is the figure that you're actually mapping? So in this last example over here, we are going to define what is a translational symmetry, which is basically a translation, as we said, that maps the figure back to itself. So basically, if you take something, if you take the figure and you shift it, then that means that the result is that it goes back in the same shape. Well, you're wondering, okay, well, how's that even possible? Because if you shift something, you can't go back to where the original position is. Well, it is possible because what if your figure is on an infinite plane? What if your figure is on an infinite plane? So, for example, let's say that I have a small little figure like this, which is going to be kind of like a, box with a kind of like a sad face right here. If I shift it over, then you can see that you have another box over here. And if I shift that over, you have another box, and then so on and so on and so on. So my figure is not just one box, but what if I have an infinite number of these boxes that are filled like this then? Because in this case, if I shift the box in any direction, then you are going to go back and map it back into, the figure that is supposed to be the set that we're actually using. Okay, so this right here, where your figure is going to be on an infinite plane, and there are going to be, like a perfect symmetry where everything fits onto the plane. That is what we call a tessellation then, okay? So a tessellation, the definition is that it's basically you're taking a piece of a figure where you're going to basically put it all on an entire plane, and as a result, they actually don't overlap. So meaning like, they basically form a pattern on a wall or something like that. Okay, so that is going to be the idea behind tessellation. So you've probably seen it before where, you have like, say, a wall with a bunch of fish, and they basically are stacked in a way or drawn in a way that they actually fit perfectly one next to another. And then it fills up the entire wall with like no gaps or anything in between. So that would be a tessellation then, okay? All right, so let's go ahead and try to look at some examples of this. So here, we're going to go ahead and see the following then, okay? So I want to know or describe the following types of symmetry that you can see in this figure. So I want to know, just like in the previous problem, where are there any kind of line symmetry over here, or are there any kind of point symmetry as a result for each one of these, okay? So let's go ahead and draw them. So in the first one, we have a rectangle, which, yeah, definitely we have some of those to work out with, okay? So here for a rectangle, I definitely see a line symmetry with a horizontal line, so I'm going to draw that right there. So that's going to be one of them. Another one would be over here, which will be this right here. That's the vertical line, and that's going to be an also symmetry. Now, if you're thinking diagonally, the problem is that if you fold it diagonally, you're going to end up with something that is like this. So that actually doesn't work out though, unfortunately. Okay. So in conclusion over here, we do have two line symmetries, right? We have a vertical line. We have a horizontal line. We have a vertical line. And then are there any point symmetry? Well, let's see. If we take the point, let's see, what can we rotate it? Well, how about right in the middle? Because that's usually a good place to start. Go ahead and call that point O right here if you want. Okay. How much do you have to rotate in order to get that same shape then as a result? Let's see, if you roll this by 90 degrees, again, you're going to get something vertical, so that doesn't work. So then that means if I roll it by 180 degrees, I think that would definitely work out. So in this case, we have a half turn. That is also going to be our symmetry then, okay? So here, that is going to be our symmetry. That's one type. That's going to be the point symmetry, the half turn. Then there is the rotation about the horizontal line, and then rotation about the vertical line. So there's a total of 3 in this case. Well, let's see. For the second one over here, this one over here, well, we can probably say it's the same idea. There is going to be the horizontal line symmetry in this case, where we can fold it across this line, and you can see that you get the same shape. Similarly, we can show it. We can go ahead and rotate it, or not rotate it. We can go ahead and fold it across this vertical line over here, and that actually works out too. But unlike the first one, it looks like we have a little bit more, because we can also fold it across the diagonal line of 45 degrees. So this guy right here, that will create a symmetry, and this guy right here, that will create a symmetry, because any one of those lines you fold it, it will just become the same thing again. So these diagonal lines are also going to be symmetries then. So there are 4 in this case for the line symmetry. As for the rotation, again, look for the center of the figure. From there, that's where you're going to rotate it. And let's go ahead and call that point O, just like before. How much can we rotate it by? Well, the rotation looks like it's a little bit more than 180 degrees. Looks like we can probably do it by 90 degrees, right? So 90 is a good point to start. So rotation, right, about point O, 90 degrees, that would definitely work. Then there's also the half turn. That looks like it's going to work out. And then if we rotate it by 270 degrees, it's also going to work. And the last one, again, at 360 degree, we don't consider, because that is an identity, which we will not consider for the symmetry then. Okay. All right. Now for this last problem, what I want to do is create a tessellation with the shape. So meaning I have a shape right here, and I want to basically fill it across the plane so it takes up every single piece of the plane without having any kind of overlap. So for something like this, what I like to do is probably draw like a bunch of these, so then that way I can see where I can match them up. So here, let me just kind of draw some on the side. So here's one right here. Okay. And then let's see, and then we have another one, so something like so. Okay, and then let's go ahead and draw maybe a couple more. So here we have another, so using a different color. And then finally, actually wait, let's make this a little bit bigger. Okay, and then finally we have a last one, which will be over here. Okay, and so remember, what I want to do is I want to basically line them up, because we're doing kind of like a translation, a shifting. So in that way, we take up the entire plane. So here, let's go ahead and maybe put it somewhere. So this is kind of like a little game of Tetris, because the question is, where do you put it? So then that way it all matches up perfectly. So here, if I put them over here, and then I take this one and put it over here, looks like that's not going to work, because you have a space that's filled. So maybe I can try to give it a little bit more space, and hey, that looks like it works. I can put this over here, and that'll work out. For this one, we can go ahead and put it down here, and then for this one over here, we can go ahead and put it over here. And let's see, can I put this anywhere else? Looks like this one's not going to fit over here, so I'm probably going to have to put it over here. So basically, you know, if you can kind of fit it all together, so then that way you can create a tessellation out of it, where all the shapes can just like, you know, be put in there, kind of like a big puzzle, then that actually works out. But unfortunately, I don't think I'm going to see that happening, because you'll notice that, okay, the red right here is probably not in the right position. So here, maybe I can put it over here. So maybe if I just, you know, stack them diagonally like this, then that would actually work out then, because then we would have something above on the top as well. Okay. All right. Well, there you go. Thank you so much for watching, and I will see you guys next time then. Okay. Take care, everybody. Goodbye.